Hey guys, I'm going to be presenting a hard to explain algorithm. It's actually a pretty simple one, but um, I remember reading it way back when I was reading through and doing the exercises in accelerated C++, and it's hard to think about. So I thought, why not try to take on the challenge of presenting it as a concept? So, um, what it is a better random algorithm. Um, excuse me. So, in C++, um, rand is their algorithm for outputting a value within the range of 0 to rand max. And um, many people want to take take this and be able to output values within a smaller range, like 0 to 10, or 0 to 100, or 0 to 20,000, right? Something like that. Um, the intuitive way to do this, but the way that isn't completely correct, is to do it like this: rand modulus n. And n is the new range that one wants to get a random value between 0 and n, right? And in actuality, it's between 0 open range n. Because when you do modulus of n, you're going to get 0, 1, 2, 3, 2, all the way up to n minus 1 and not n. because of course n modulus n is back to 0. So um, how can I keep explaining this? So that's part of it. So the reason why this solution here isn't completely correct is because um, some values that are outputted are more likely to occur than others, and the larger n is, the more that disparity, the larger uh, the disparity of values being more likely to occur increases or becomes larger. So, of course, a good way to think about this is to visually show it and work with an example. So let's say n is 1,000 and rand max is 33,500. This changes given your C++ implementation. So um, imagine here we have the beginning and the end of our range from 0 to rand max, and I'm just going to draw it out here. Alright, cool. So rand is going to be, when you call rand, it's going to drop values randomly, right? They're kind of raining down here, and so any value can come down, right? So what modulus does is it essentially, you know, um, cycles through whatever rand outputs and gives the modulus of n. So um, Each of these are the divisions of n into rand, right? And when when you do the modulus, you divide something until you can't divide it into any more equal parts, and you get the remainder, and that's what the modulus is. So, if we're looking at something like this, let's say the number that was dropped by rand was 10,500, then the modulus that comes through is 500, right? If it's 4,900, of course the 4,000, this would actually be 2,900, but it's just for show. So let's say this is 4,900. The modulus would be 900, and so on and so forth, right? Until we'll do some dot dot dots, and this will keep on doing its thing until the very end. But what happens is when you look at the potential modulus values upon when you do what rand outputs modulus in, the last modulus cycle here, it only is able to do half of the numbers, right? So these other numbers, they aren't given a chance to occur as equally as the numbers on this side. So you can kind of see how the values from 33,000 to 33,500, they're when they have modulus n done upon them, and n is 1,000, that means that 0 to 500 is a little bit more likely to occur than a little bit more likely to occur than 500 to 999. And so it's a little bit more likely to occur. Maybe you're okay with that, but people that get into engineering things, they want to have things be correct and such. And another thing of note is that the larger n is, the greater the disparity of some numbers being more likely to occur than others is. So, and I think I don't think that's not that's an approximate statement. I think as you make larger n as you make n larger, sometimes all values will be equally likely to happen, but as you increase n, depending upon what n is, you could have a ton of values be more likely to occur. And the best way I can explain that is if you're getting modulus of 16,750, or rand modulus 16,750, then that actually will lead to equal dispersal of values when you do rand modulus 16,750. But if you do rand modulus like 20,000, you're going to have um, uh, 0 to 19,999. Those values will all happen once. The values from 20,000 to 33,500, which when modulated would be 0 to 12 or 13,500, would occur, and the other numbers from 13,500 to 19,999, those would not occur. So all those would be half as likely to occur as, you know, the original 13/20ths. Hope you guys are following me, but I'm trying to maybe more visualize or verbally explain how this original intuitive Rand algorithm here becomes less correct and more volatile the larger n is. So, gosh. Okay, well, hopefully, I think I went off the deep end there with explaining it. I think I did a good job, and I was pretty accurate, but it's a little heady stuff that I explained. So, moving on. The solution is to do this. Find a new range. Find a new range, which is 0 to some number where that range can be divided into equal parts of size n. Thus, when you do that, doing any value that drops within this new range and calling modulus of n upon it results in outputted values that are all equally likely to occur. So to explain it more, we want to, going on with our example, we want to find a new range that can be divided into equal parts of size n. Well, that is 30. The range is 0 to 33,000, right? And it creates that. It creates those. It creates a situation where any value within that range that is modulated, the outputs are all going to be equally likely to occur. I keep on saying that. I'm beating it like a dead horse. So, yeah. Another thing I gotta say too is, and just it's something that's true that we want to take into account here, is that we're gonna keep looking at what Rand outputs when we call it, and we're only going to look for values within the range. We're not, if Rand outputs values over here, we're not even going to think about them. We won't take them into account. We'll throw them away within our algorithm. And that's it. Let's write out the pseudocode. Rand max. So we're going to divide Rand max into n, which is, because we want to get, once again, n. What is this n that we're discussing? N is the range that we want to get a random number between, right? So we do rand max divided by n. So we're going to get n divisions and some remainder, right? But the way that code works by default is it truncates this division here. So we're actually going to get the amount of parts of rand max that are divided by n truncated. So we'll get the whole parts before the remainder, and we're going to multiply by that by n, and thus we have that new range that we're looking for. Right? And then we're going to do, we're going to set up an int val that we're going to pass into a do loop, and we're going to say do val equals rand while val is greater than or equal to new range. So this is our method of disregarding rand outputted values that are over in this section. So, we're going to keep on getting rand values until we get one that's within the new range that is equally divisible into parts of size n. And then we'll do this. We're going to return val modulus n. So we got our val, it could be 23,023. And when we call modulus, modulus n of val, or val modulus n. So 23,023 modulus n modulus 1,000. That's going to be what the remainder is when we do val divided by n, which is 23. And to wrap it up and summarize and conclude, what have we achieved? We've achieved an algorithm that will always output random values within a desired range that where those randomly outputted values are truly random, from the mindset of them all being as equally likely to occur as the other. Okay, I think I did it. I nailed my acrobatic jump, my presentation. This was my third time doing it. So maybe this is the one that'll post, or it'll never reach the light of the internet. Cool. All right. Bye-bye.